Hello everyone, welcome at Somnia and welcome at the Data and Drinks. I'm Nelleke, I'm a machine learning engineer at Somnia and today we have two interesting topics. First up we have Shadi, who is working at Slimstock, who will tell a bit how they implemented their machine learning libraries in their current software stack. And second up is Rogier, who is a freelance data architect and will tell us a bit more about cloud analytical databases, where they should be used, how they differ, and how they are similar.
Hello, everyone. My name is Shadi Al-Ghawili. I work at Slimstock, and I'm a machine learning developer. And I'm here today to talk to you about developing a machine learning library in an existing software product in a very unusual way, which I like to call the road less traveled. So today I want to talk to you about a few topics. So first I'd like to introduce Slimstock and our software product Slim4. Then I will talk a bit about the machine learning library that we implemented in Slim4. And then I will discuss three challenges that we had to overcome with good things and many lessons learned, and also things that we are still not sure about whether it was the correct decision or not. And finally, I would like to actually end this talk with why I gave this talk instead of at the beginning, and hopefully it will become clear at the end. So Slimstock is a company based in Deventer, and we are experts in inventory optimization. So that means everything related to how much to order of which product, when should you order it. To keep your inventory position healthy, you don't want to keep too much stock, but you also don't want to have too little stock, because then you cannot sell it to customers. We have around 1,300 customers worldwide, and that's everything from retailers to wholesalers. So big companies where retailers order, for instance, manufacturers of all kinds of products. And these are some of our customers. Just picked a random few. We started 30 years ago, and we have around 400 employees worldwide in 23 offices, but the headquarters is based in Deventer, city in the Netherlands. And as you can see, we have offices all around the world on every continent. And we are hiring. So if you're interested, just go to the webpage. We have many different roles. You might be interested. Always good to mention. So we developed a software product, and that's called Slim4. And that's basically a software product that customers use to optimize their inventory. And every business is different, so every business may have different decisions that they would like to make that's relevant for their business. We also offer consultancy and training, because at Slimstock we believe that the better the customers we sell the software to understand the software, the better they will use the software and reach results. So actually, when you buy our software, you also get the free training and masterclasses and so on. And it's basically based on methods from operations research. Some of you may know this field, but basically mathematical formulas to optimize future processes and business rules. But we are now introducing machine learning into Slim4, and that's where the research team came in. This is a screenshot of our software. So when you open up the software, you get some KPIs about your inventory position. Companies typically have anywhere from 10,000 different products, maybe to up to millions of products. And this gives you a clear overview, and you can drill down and so on and so forth. And basically, this is an overview of a certain product in the database, and you get the historical demand in blue and purple, and the forecasted demand based on the operations research models in yellow, and all kinds of metrics related to the inventory for this specific product. And of course, you have many tools in the software to find products, filter products, and so on. Now, the research team consists of small team of data scientists, machine learning developers. We started 3 years ago, and we do many different things. But I think the most important things are we build prototypes in Python. We run pilots at end customers of Slim4 to evaluate prototypes. And then we bring the prototypes that are working well into our production software in Slim4. This is the team, and next week there will be a sixth person on this slide as well, but starting next week. So machine learning in Slim4. So our goal is not to simply bring machine learning just to have it, but we want to use it to automate and improve processes for inventory optimization. There are certain parts of Slim4 that we cannot automate yet, or it would be too time consuming to do manually. And in those areas, machine learning could really help, either by solving the problem outright or by minimizing the manual time that customers need to apply for certain products. Now, we are working actually with quite, as I would like to call, vanilla machine learning. Standard algorithms, nothing too fancy or complicated, tabular and small to medium-sized data. But we are working in a very non-vanilla environment because, partly because Slim4 is based on a Java computation engine, and that Java program exists already for 30 years. So there is not, it's not a greenfield project. We have all kinds of constraints we have to be taking into consideration when developing the new machine learning functionality. And this is also very particular for our business, is that our customers install Slim4 software on their own on-premise server, on their own hardware, and using their own data, for example. I'll dive more into that later, but that basically means that every customer has the same database schema, but the data in that schema can be different is actually different for every customer, and it may even be in different languages and so on. So that's why I describe this as a non-vanilla environment. And we are interested in the end-to-end machine learning workflow. So that means everything from configuring what the machine learning models should do, to training and inference, analysis and monitoring, because we believe that all of those things are important to implement machine learning successfully. Now, we have recently, end of 2022, released our first application, machine learning application in Slim4, a transaction outlier detection. And that basically means detect and exclude abnormally large transactions and exclude them from forecast of the demand. Because such transactions lead to, if you keep those transactions in your forecast, then you typically forecast too high. And that means that you keep too much stock of a certain product, and that's expensive. So you would like to, optimize that inventory position. And we do that by training models based on a flexible configuration. Because, as I said, like every customer trains models on their own data. So for every customer, what is important for their products differs. So some customers may have many promotions. Some customers may have atypical demand patterns or seasonality. For example, we have customers worldwide. So that means that the bank holidays, Christmas, is maybe relevant in Europe, but in Asia, there are different holidays. So you need to be able to specify and configuration and select features and so on. And basically, again, they do it on their own hardware as well. That's also really, I think, an important topic. Now, that looks a little bit like this. So this is a screenshot from actually Slim4, where you get this configuration screen to set up transaction outlier detection. And I think the most important two factors here are the outlier threshold. So how much of your demand do you see as extreme? In this case, 1%, 1 minus 99. And which features are you going to take into account? And those features are selectable based on the filled data in that customer specific database. Now, when you train your models, I hope it's a bit clear, but you can see the demand graph for this particular product, and you can see that some of the transactions were flagged as outliers and therefore excluded and have a different color in the graph. And that basically means what it means for us for a machine learning model to have made predictions for this particular product. Now, there are many other very interesting machine learning applications in the inventory optimization field. So we can think about forecasting demands for products in promotion, which we are currently developing, or for newly introduced products, because you don't know if it's a completely new product, you have not seen any previous demand, but you still need to stock something. So how much are you going to stock of this product? And that's also a very interesting application of machine learning. And because of that reason, we are developing a library, what we like to call it, of reusable machine learning components, so that we can not only make one application, but actually make a lot of different applications without reinventing the wheel every time. So that means flexible machine learning pipelines of transformers and models, cross-validation, feature engineering, model monitoring. So many of those components are not very specific to one specific application, but can be reused. Now, that's a little bit so far about what we are trying to do. And now I would like to continue the rest of the talk with discussing why that is not so easy under these circumstances, or what challenges we have come across when doing this. And one really important factor in that is that Slim4 runs on-premise frequently on a single machine. Even though we have a cloud option available, many customers choose to keep their software on-premise for a variety of reasons. So some customers, not all the customers are in Europe. So there are differences in technology maturity, let's say. But there are also, one of our customers is the Ministry of Defense, and they don't have an outside internet connection. So there are a lot of considerations, and every customer is different in that sense. But still, we would like to offer machine learning to all of our customers. So this is a constraint. And that means that these machine learning models are trained on limited hardware and potentially old software, think of old SQL versions, stuff like that. And the current development team and all the processes, including security updates, dependency updates, it's all based around Java, because the software exists for 30 years. And sometimes we also have limited control over the customer environment. So they might be sharing the same server for multiple applications. So we cannot just take all the available RAM, because that RAM may be used by other applications as well. So that's also a consideration. Now, given these, given this business environment, which aspects would you consider when choosing the software stack for machine learning? So maybe if somebody has some ideas of things that you may want to think about. Yeah.
I think the machine learning model should be decoupled from the rest of the application. So you should approach it by an API maybe or something.
Yeah.
You're limited to Java at the moment, but I don't think you want to use that maybe for machine learning.
Yeah, that's a very good point. So I think, I'm not sure if everybody could hear it, but basically I think you're saying, why don't you separate training machine learning models from the rest of the application, for example, by introducing an API? That's definitely also one thing we considered, so I'll get back to it. But are there any other suggestions? Yeah, can you?
Architecture should be easy to use, easy to maintain, and easy to scale.
I'm not sure if I heard you correct, but easy to maintain, easy to secure, and easy to deploy, or?
To secure for the large, different amount of data,
Mm.
and from several thousand to several million.
Yeah, so that's indeed the case. Also, some customers have very few data, like actually could be anywhere from a couple of thousand rows to some customers have enormous data. That's definitely true, and that's also something to consider. Yep.
Customer data security would be the highest part to me of big importance.
Yeah, so that's data security is an important topic for some customers, even more than others, I would say. But that's indeed why many customers train locally. If you would make an API, then you do need to think of the security implications for that as well. So it is one thing to consider as well. Yeah.
The software itself has to stay in Java or something like that?
That's a good question. So the question is, should the software definitely stay in Java? And that's, I think, in principle, open for debate. On the other hand, you do need to keep the shop running, as we like to say. So we have, considered this, but it's not immediately clear whether you would then stop all the new developments in Java and create a new second team, or you do it simultaneously. And I think as a company, we need to, maybe grow in that as well. It's not typically machine learning problem, but definitely something to consider as well. So we when I thought about this slide, I thought that basically there are three important subjects. So there's the technical side of things. So is there, like any kind of software stack you're going to choose, you want to have some synergy. So do the different libraries work well together? So in Python, that works amazing. In R, that works great if you don't do production. But there's also the issue of like ease of use. Like, are the data scientists using this library? Then it's easier to use, of course. Maturity of libraries, that's important for us for security, for instance. So if nobody is really monitoring and updating dependencies in a library that we're using, we cannot use that in production. It should be easy to maintain. Python is great for that. And iteration speed, of course, Python and R are great for that. But there are also operational constraints. And that means, for example, when we install our software at customers, it's a manual process still. The updates are automatic, but when somebody buys Slim4, a consultant physically goes to the customer, connects their ERP system to our database to load the data into the database. And it's basically like installing software on a Windows machine. And that means that we have to minimize the maintenance and the configuration on that customer's machine. That has implications for deployment, security updates, and stuff like that. And furthermore, we also have the organizational constraints. So how does the existing team look like? What is the existing process? How difficult is it going to be to hire new team members? So, and that relates really to the software exists for 30 years. The entire stack is based on Java. The entire development team is in Java. So you can do it. Python API is definitely something we considered, but that's although technically the best option, I would say, my personal opinion, but organizationally and operationally was more difficult to implement. So we actually did it in a completely different way. For better or worse, we did it in Java, and that's the rest of the talk is basically gonna be about that. Because machine learning in Java is possible, but there are limited options of doing it. And the biggest challenges we faced, basically, as a data scientist coming from Python or our background, is that it's not as well maintained or documented as all the libraries that are out there. It's not very easy to find out how it works, how it's supposed to work. It's lagging behind in new developments. So we are using XGBoost, for instance, and the Java API for that is maybe 1 year behind the Python API. So all the new functionalities are not immediately out there. There's a lack of synergy between the libraries. So if you use XGBoost for J, for instance, and you try what we do, we use Spark as well. Those two don't necessarily talk to each other, whereas each of the libraries doesn't have all the functionality that you need. Yeah, and it basically have smaller development communities as well. So there are basically lots of question marks in Java that you have to figure out yourself. So it gets worse in a sense, because in the end, we looked at all the available options in Java, and we figured, okay, Spark, it's mature, it's well maintained. The things that are in Spark, they work well together. So let's use Spark data frames and Spark machine learning. Basically, because there are not many alternatives. but it is missing some components, so we do need to develop some stuff ourselves, and maybe use some libraries here and there as well, so to connect them together. But what makes it worse is that we are doing it on premise, right? So as I said before, the application runs in a single machine, and Spark is designed to do things on a cluster. And if you don't use a cluster, you can still use it, but it comes with a lot of warnings that you don't necessarily know why are they really warnings. So we are, and furthermore, we are working with very small data, so we don't really need Spark. But yeah, just because there's no other option, we are still using it. That sounds harsh, but like given all the other considerations. But an example of this is that if you look at some Spark books, they might say, okay, we do not recommend using local mode for production. But what does that mean? So you may find some Stack Overflow question and it has one answer, but that answer happens to be given by me. So they're not, that doesn't make you very wise. Then there's the Spark performance. So we are working with small data sets. And if you use a distributed compute framework with small data sets on a local machine, then you're going to have high overhead. And that means, for example, that if you have like 5,000 rows in your data set, you expect a simple count to take maybe 100 milliseconds, but it might take 2 seconds because there's a lot going on inside Spark. So although our data sets are small, it probably will come later, but it will be good to mention at this point as well, our customers train models for each product. So although the data set per product is very small, there may be tens of thousands or even hundreds of thousands of models for that particular customer. So 2 seconds times 100,000 is a lot of overhead. So we have to deal with that. And it makes you very creative in how to calculate counts, how to avoid counts, how to do things outside of Spark that you don't need Spark for. So it's a little bit like you want to be using something, but it's not really made for it. So you start to build around it and it works, but it's not ideal. And what makes it even harder is that Spark is lazy. That means if you apply several steps in sequence and you try to measure the performance between 2 different steps, it's not necessarily that step has been computed yet. So did your code make it faster or not? Or which step did get faster? So that's also difficult. So it basically took a lot of time to get transaction outlier detection performant. And basically it works. It has now decent speed. Transaction outlier detection is in there. But it's definitely a road not well traveled. There are a lot of unanswered questions, ambiguity, and requires figuring things out yourself. And using it, the ecosystem is not really intended for our use case, but there's also not really that many alternatives. And that's why we're still considering a Python API for the future. Now that we have an application in the software and customers are using it, then there's also a bit more credibility that you have in the organization to maybe push some of these bigger changes, because in the end, this is not ideal. Now, the second big challenge that we encountered is, again, good to discuss with the situation. So our software Slim4 is updated every 3 weeks, and that's an automatic process. So basically, there's a scheduled task that runs every 3 weeks to get the new software version. But models are trained per product, as I say, so maybe in the order of tens of thousands of models. And therefore, frequent retraining is not possible because it takes a long time to train all of those models. But the lifetime of those models is longer than 3 weeks. You want to be using them longer than 3 weeks. So we need some way of saving or persisting models across Slim4 versions, basically backward compatible models, while still retaining the ability to update and refactor our code base. Now, there are some requirements for such machine learning models, in our opinion. So there needs to be some kind of consistent behavior of the entire pipeline between Slim4 version. If I train a machine learning pipeline in version 1, then I still want it to work in version 3. even though the software may have changed, like in terms of the class may have moved to some different package, I don't care about that as a customer. I still want my machine learning model to work the same way. So that's what I mean with consistent behavior. And the ability to refactor means we should be able to reduce technical debt, change class or field names, move classes around, and so on. And it should not be exclusive to a single library. So we could be using the library save functionality maybe, but we also have our own transformers and we may be using different libraries. And those still should be packaged together, let's say, so that they can be saved and loaded together because the whole pipeline needs to work. Now, we looked at different options and basically came to the conclusion that it's not so easy as you might think. Because one thing you could do is in Python you have pickle, so you would think, okay, let's do pickle. But that in many cases breaks the ability to refactor. So if you're not careful, you store the entire class in pickle, then you change the class structure and load it back into pickle, it won't work anymore. Or if you move a class in a different folder and you try to load it back, it won't work anymore. And in Java, you have what's called Java serializable or different serialization mechanisms. But basically, the same issue occurs there. If you change the name of the class, you can't load it back in. Stuff like that. Now, the second option would be to look at, we are using primarily Spark. Spark has a save and load mechanism, right? So why don't we use that? But our software is installed on Windows machines. And then you find out that Spark was designed for Unix systems. And if you want it to work in local mode on Windows, you need a specific, external, unofficial dependency that makes it work on Windows. And that has security implications. And there's also bugs in those kind of packages, of course. So now, and then you can have specialized libraries such as MLlib or maybe MLflow or maybe PMML, so like you have stuff that works with this. And we basically decided to combine options 2 and 3. So we looked at the Spark internal, so how does Spark actually save and load models, and how do these libraries save and load models? And we copy basically what we can, and for our own stuff, we implement the same mechanism, and let's see where we get. And basically, the essentials about backward compatibility in our experience is that you need to save only what you really need. So if you are talking about a linear regression model, for example, then you may want to store the trained betas, but you don't want to necessarily store the business logic on how to output the results, for let's say, because that's not actually physically part of the model. So if you separate the parts that you need to save in order for the model to work well from what you don't need, then you allow refactoring without affecting the saved models. And basically, you can make that work, and that's how the libraries do it, roughly. So you define a schema, so that could be JSON or XML or whatever. And then you save the specific model parameters that are trained to that schema. Because you know the schema, you know how to serialize and deserialize it. So when you are trying to make predictions, you retrieve the saved object and deserialize it and use it to reconstruct a pipeline from the trained parameters. And then you basically implement a save and load method that reads and writes to that schema. And then you maintain the schema. And it would be great if you can rename parameters or change the schema in a backward compatible way. And for that reason, we used something that's called Google Protobuf. And it's basically what I like to call JSON on steroids, because, for instance, it's typed. So that helps in Java because it allows you to auto-generate code for getters and setters to the schema, basically, for instance. But it also provides backward compatibility. So that means that you can change the parameter names, you can introduce new parameters, you can specify default values for new parameters, you can deprecate parameters. So that helps, because if you want to change, you want to introduce a parameter, but you still want the old models to be loaded well, then you can specify a default parameter, what it was in that version. And you don't have to have too much boilerplate code, like if version 1 is this, then I need to do this, and so on. And this is how that would look like for a decision tree. So a decision tree as part of random forest basically consists of this essential data, and you can store that data in this schema, and then you can load it and save it. That's how we did it basically, and then the stored object can be saved to a file or to a database or whatever. So yeah, and then the final challenge that we had is automated testing. So in software engineering, this is a mature practice, but I would say that for machine learning, it's not necessarily as mature as it is in software engineering in general, because you have to deal with many more factors. You're dealing with randomness, so maybe you need to choose your sample size wisely. So you're creating a test that tests some cross-validation behavior, for example. Then, yeah, you need to choose your sample wisely so that the results actually test what you are intending to test. But then there's also many other factors involved, such as data or the hyperparameters, configuration. So choosing useful and conclusive scenarios is not always easy. And they might not even be always observable. So some of the test scenarios may involve like measuring the RAM or the CPU usage, stuff like that. Yeah, that's not always so clear and very important, I would say, in machine learning, in our case at least. So in my opinion, code coverage in such a scenario also doesn't say much, and it's really have to think about, okay, which tests do we actually need to make sure that our software and machine learning models are doing what they're supposed to be doing. Now, what did we do? So we have some isolated or integration tests of like machine learning components and business logic. But relating to the previous point, we also test whether a dependency update of Spark doesn't break our saving and loading mechanism for backward compatibility. We also have regression tests, so if you train a bunch of models on known data, do they still give the same results? So we didn't mess up something in the pipeline logic. And we are also working on performance tests in an automated way. But yeah, why this talk? I know the talk is almost over, but I do want to leave this last slide because, in my opinion, how we want to do ML and how we should do ML according to the books and the talks and the YouTube videos, there's a very large distance between those, because in practice, I think a lot of companies are in the middle column, such as from proof of concept to production, or you're using a non-vanilla use case, or you have an existing software stack like us, all kinds of organizational constraints. So how we want to do ML and how we should do ML is not really always that clear. And I think we should teach overcoming everyday practical challenges much more than we are doing currently as a field. Because, in many cases, you don't have the Greenfield project or the Kaggle competition situation. And yeah, we should teach it in a more full stack way. So I like to see data science and software engineering and the domain and the organization much more as an integrated whole to do it well in, let's say, real life, more than proof of concept situations. And I gave this talk because I couldn't find this information anywhere. And I'm sure I can't be the only one who feels this way. So yeah, if you feel the same way, get in touch, feel free. I think we definitely need to we need to do a lot of work to implementing machine learning well as a field. That was my talk. So thanks for your attention.
Hello, good evening, everybody. Welcome to my talk. I'm Rogier, but a little bit more about me in 1 second. My talk will be a complete change from the previous one. It will be about cloud analytical databases. It's a little bit different than the introduction. It's not that I'm going to talk about what the difference is between analytical database and operational database. I can also talk about that if you want, or you can ask a question. So the main topic of this talk is actually comparing these systems from Google BigQuery, Snowflake, Redshift, and Azure. And then we'll talk a little bit later, we'll talk about why I made my own comparison. And as this is a sort of living document, a work in progress, I started due to high demand and folks starting using Databricks, Delta, Photon, whatever they want to call it today. also for the data warehouses. So that's still in progress. It's not finished. I've already working in this field since October 1999, so I consider myself old, and looking at also in my daily life when I work at my clients, looking at the people that surround me. My current assignment is in healthcare, so there are a few people that work in that domain for longer and are actually older than me. So I don't feel like at the end of my life yet, but it's getting there. And so after working years and years for different companies, a few years ago I started freelancing. So currently I work in a sort of hybrid data architectural, data modeling, product owner, analytics engineer / Snowflake configuration person. That's what I do. And next to working, I live in Utrecht. Sometimes I give talks. And I don't work as a machine engineer, machine learning engineer. I know a little bit about data science. So my core focus is really data warehousing, data architecture for data warehouses. As such, I do like data warehouses. That's basically what I do. But why did I cross this out? There's an important thing about, does somebody know what a data warehouse is about? What is data warehousing about? And why would I put down this quote? And who actually said this? Any idea? What kind of person would have said, if you cannot build a data warehouse, you shouldn't do AI? Would that be a data warehouse vendor? Would that be somebody else? No? Yes? You know. No, it's not Bill Illman, it's this guy. So, do you know this guy? Yeah, you all know this guy. Who is he? Yeah, exactly. So that was interesting a few years ago when I heard Andrew Ng actually proclaiming this. I think it was somewhere at the Strata conference. So where he sort of written and gave a talk about, if you cannot build a data warehouse, you shouldn't do AI. So why did he do that, you think? Any ideas? Well, the purpose of a data warehouse is that you think about data usage and data consumption and data structuring well, and that you can collect, integrate, reform data, often raw source data that is a horrible nature, horrible structure if you actually want to use it for reporting, but also for machine learning, right? We all know that you spend most time on things like integrating, cleansing, and feature engineering. You could also, that kind of work is part of data warehousing. So that's what a good data warehouse, if you build it, should do. Where do you build a data warehouse in? Using different tools and technology. And one of the things you need to build a data warehouse is, well, you can do it on premise with your single machine if you want. Nowadays, a lot of companies choose to go to the cloud. You can, even in the cloud, you can spin up a single node SQL Server, Oracle, MariaDB, SQL Server, whatever you want. You can also choose to take native cloud-based analytical data warehouse. And that's interesting. They say analytical data warehouse. A lot of companies selling technology, they sell this technology as data warehouse, but as data warehouse is something that you build, and what they sell is technology, a database, tools around it that enables you to build a data warehouse, and those kind of things are often horribly intermixed. So if you want to build a data warehouse, if you want to do AI, and if you have, so one of the questions, and that is not part of the talk, but I was to do, why to choose an analytical database versus a single node, MariaDB, SQL Server, whatever. Any idea? yeah, the main reason is scaling, size, basically the premise of being able to grow forever in amount of looking at the amounts of data and the amounts of compute that you can throw at it. There's no need, obviously, if your company is small, your data amounts of small, it can still make sense to also not use that large-scale cloud-native analytical database, right? So, but if you do, then the selection of systems to choose from is basically endless. A few years ago, I've worked with Google BigQuery first. Later on, I did a migration from Redshift to Snowflake. I've worked a lot with SQL Server, and SQL Server's implementation of its analytical database is kind of similar to the on-premise version. But still, if you go to a new client and you start greenfield and you don't have something yet, then obviously the question is, what do you choose, right? You can go to the Gartner ways for cloud data warehouses. That's at least is there in their official papers, but obviously it should have been called cloud analytical databases. And look at these kind of quadrants, and yay, they're all leaders. But then, what does that mean? What does that mean? What to choose? Obviously, you can pay for additional context that these reports always have, like gazillions of dollars. You can look at other quadrants from Gartner. Yay, they're also leaders too. You can look at what customers think about it. Yeah, it's G2 Grid. A lot of customers that give their ratings are paid to give their ratings. So how honest is that? Are those ratings? You can look at, and I still advise you to do this. I still find the most reason if you're gonna make a technology decision, don't only go by your gut feeling and what you need or people around you. Still use this information, but this is not enough. You can use DB Engine Trends, interesting website where you can just query them all together and see. Note that the scale is logarithmic though, on their popularity. What happened here with Snowflake? No, they were in the cloud since the beginning. What happened here? Sorry? No. The IPO, yes, indeed. The IPO and DB Engine Trends. What's interesting about it that they collect it. It's basically a sort of popularity contest for data. So they collect data about a lot of things, about how much is written about the system and the Stack Overflow, etc. So it's kind of a sort of most honest comparison about how popular a system is. Google Trends, obviously, you also know that. So there's lots of ways to do that initial comparison. Short overview on these systems, what I have to do before I start with the rest of my journey. How much time do I have officially? Around half an hour, okay. From now? So originally this talk is an hour, so I'll have to skip some slides, so do know that. BigQuery, system from Google since October 2011. Anybody works or worked with BigQuery? Yeah. Okay, cool. What do you think about it?
I honestly love it, but we don't use it anymore. I used to.
Yeah. I personally also love it, and I love it. It's one of the systems that is also really cloud native, and one of the things that really makes it unique, that Gmail kind of functionality of no nodes, nothing to configure. That's quite, I think, there are more systems that do it somehow now, but I think, in my opinion, BigQuery is still unique. So if you need no configuration at all, and if that's your most important selection criteria, then, and if you're allowed to use Google, then that could be a way to go. Then we have Redshift, that is the oldest kit on the block. Even though it says here that it's in since October. I think this has something to do with availability being internal or external or something like that. At least now that Redshift was one of the from Amazon was one of the systems that basically went popular first, especially in the US. Here in the Netherlands, it's not used by a lot of organization. So what makes it unique is if you need a lot of knowledge, and if you don't work in the Netherlands, then most knowledge, for instance, resides in the US, and because it's based on Postgres, it has excellent SQL support. Another one, Snowflake, the one I currently work with my current clients. Since October 2014, it's been available. Also born in the cloud, so it didn't exist on premise. It doesn't have any legacy, and what it makes it unique are a few things. Is that it's really cloud agnostic, so it means you can run Snowflake on all major cloud platforms with the same UI and functionality, and things like, for instance, no downtime, auto scaling. What does that mean? If you run a warehouse, if you run compute, if you run queries, and you want to increase the size, you want to scale up. No, you want to scale out. You want to make a single node bigger. So, for instance, from an 8-core machine to a 32-core machine, you can change that while queries are running, and nothing is interrupted. So that works seamlessly, and that's one of the great things that you don't find on obviously in BigQuery, where everything is completely services. There it doesn't apply, but in comparison, for instance, with the offerings from Amazon and Google, and also Databricks, it's definitely different. And stuff like that, I personally that is very attractive if you want to, for instance, spin up a test environment that is based on production. Is functionality like metadata-based data cloning, where you basically don't copy your data, you only copy your metadata, and with that you can then work further. Azure dedicated SQL pool. With Microsoft, my opinion is that it's in how they name products is really complicated. At first it was Parallel Data Warehouse, then it was SQL Data Warehouse, then it was Azure Synapse Analytics or something like that. And somebody told me that now I should call it Azure Dedicated SQL Pool. I'm not sure whether that is really correct. Correct me if I'm wrong, but I honestly don't really know. But it's Microsoft's native part of Synapse data warehouse or analytical database offering, and unlike for instance Snowflake and BigQuery, it's based on legacy non-cloud based MPP data warehouse stack, and it has been through a lot of iteration. One of the advantages is because Microsoft, looking at the ecosystem, especially in the Netherlands, we're an Azure country, so there is this tendency to then choose what is most natively, which is then something to look at first. I thought it was maturing. I'm not sure. Didn't hear a lot about it in the last year, so I'm not sure whether that's still really up to date. Someone working with this in one of their clients?
Well, they're scaling up the number of vCores, and the scalability was increased. First it was like 40, now it's doubled, and now it's doubled again or something.
Okay.
So they make it available that you can scale further, but there are different versions of SQL Server.
Yeah.
But of course you need to pay for it.
Yeah. Oh, yeah. But I mean, Snowflake and Redshift are also not free, right? But
so the scalability increases, but I don't see any improvements in
Okay.
functionality.
Okay. So is somebody working with, I didn't ask that, with Snowflake here? One. Anyone else? A few there. And with Redshift, probably, oh, still a few too. So it's a, but I think the most hands I saw, you work with all three.
No, I just
At the same time. Okay. And finally, what I started adding is Databricks, Delta tables. Databricks also confuses me in how they name their products personally. I find it, obviously we know it's based, the compute part is based on Apache Spark. And then you have basically their Delta table functionality with the Photon execution engine or something like that. That's, no, I'm wrong. Okay, that's basically the database part, and yeah, it's a battle, and it will continue probably for the coming years. So now, if you have come to an organization and there's sort of not people that already made up their mind how you're going to choose, right? Other than looking at the Gartner quadrants. So one of the things you could do is sort of compare yourself, do an honest comparison on the features that you or your clients find important. So the things that I present now, they're just an example. If you look at your client and what is important, it could be something specific as you need to be compatible with Java or something like that. It could be. Then that could change your criteria. But still, things like co-scaling, how you actually work with the product, what's your development experience, what functionality, what features does it support, and obviously, and especially in the Netherlands, and also if you work in the cloud, right, everything that relates to data security, privacy. So let's look at let's compare a few things. I do want to say, and this is sort of more a side project, and keeping this 100% up to date, no guarantees. It could be that some things are already outdated. So check the data when you get this. Okay. So from 3 to 1. So for instance, my client considerations were privacy is the most important, cost the last important, then speed, scale, then how you develop with it. So the order in what is important could be different for you. So I'm not going to talk fully through this table, because if I'm going to discuss every cell, then that takes a lot of time. But on average, what I can say about all these kind of systems, that if you look at the data, and if you look also at a few of the benchmarks, and if you do the benchmarks in an honest way, which is often not done. For instance, I think 2 years ago, I saw a piece on LinkedIn from Firebolt, and Firebolt was sort of they were very aggressively on Snowflake, where they claim to be a factor 100,000 to 1,000 to 20,000 to 50,000 faster for the same amount of money. And well, if you think logically, that's not possible, right? So there must be a caveat. And there was, which I will tell about later, because then my half hour is already gone. But on average, if you use it well, all these systems, until now, you can say that the costs are in the same range, which would be logical, right? Because if they really would fundamentally differ, then one would sort of push the other ones out of the market. If the costs were really an order of magnitude 10, 100 times, then that just wouldn't work, right? So all can start with fixed license. There's no cost to get started, right? Separation of compute and storage, that's all done. The complexity of how to calculate cost and predict them, that's one of the big challenges, and depends on the different modes that you run these databases. And for instance, a system like BigQuery that I told, if you use it in sort of the flat rate mode, then it's really easy. But and there's some other system that it's some other configurations that it's really easy. But in most cases, it can be quite complicated too. There's a whole ecosystem of tools for costs, calculation, and prediction around these systems. Databricks just started. It's complicated also. I'm still not sure. I do know that there are a lot of ways to tune your setup, which is nice, but also makes stuff more complicated, right? For instance, if you compare it to that BigQuery where there's no choice. So that's also how much knowledge do you have as a team to choose the right setup. Yeah, so sort of the summary, there's some systems like, for instance, the old school Redshift, and there's still customers, for instance, in the US probably running that way. You didn't have separation between storage and compute. And yeah, that sucks, right? One of the reasons to choose these systems, if you can are able to scale storage and compute independently of each other. And there's some other caveats. Like I said, it will not be always cheaper than running on-prem. If your data amounts are relatively small, then you don't need to be hip and go to the cloud and use these kind of systems. But what are your data amounts? Do you have 1 gigabyte, 1 terabyte, 10 terabyte? Do you expect to grow to 100? Do you have a lot of different consumers or not? Do you want to separate everybody out from each other in the way you consume data and don't interfere with each other's workloads? Yeah, then it's, if you're more in the latter direction, then it's a good idea. In the end, it's about calculating the total cost of ownership, right, which is really complicated. Scaling. Well, here you see kind of a difference starting to emerge that sort of makes me want to say that I prefer Snowflake and BigQuery and don't know yet about everything about Databricks, but you see in the other systems that and it's no coincidence, right? These systems were based on more old school legacy on-premise tech, and they still inherit a few of those traits in the way they can scale and resize. And overall, just BigQuery and Snowflake have better papers for that. Obviously, you won't run out of storage in any of these systems, and you have these kind of features again in BigQuery that if you use it in that Gmail kind of mode, that you actually, compared to the other systems, get a lot of compute for sort of the same amount of money. I personally also really like Snowflake as it's, for instance, compared to Databricks and Redshift, quite easy to set up and configure. And there's these kind of things like, for instance, I'm not sure whether it's still the case, but a system like BigQuery, for instance, because it is serverless, incurs for every query a 1 to 2 second startup time, and you could maybe that's not actually not what you like if you run a dashboard that actually has 10 queries under the hood that separately fire. But then there's always different components, obviously, that you can stack on top of this technology to make performance bottlenecks go away. One of the things with these kind of choices is if you go to the cloud and you choose a system and you invest a lot, are you gonna then switch? If you're in Snowflake, are you then gonna switch next year to Redshift or to Azure? What would be the rationale? it's always costly to migrate. So if you're going to go to the cloud, choose wisely. One of the other things about these kind of systems, and why, for instance, migrations from on-premise can be complicated, because this technology also enables you to work in different patterns than you're used to, because you're able, for instance, to scale out and up your compute. So the way you design your whole data pipeline could change. And if you want to leverage the advantages of these kind of systems, then I personally don't believe in lift and shifts from old school on-premise system. Maybe for a proof of concept, but I think it's always better to refactor. And obviously you have the danger, and I've heard multiple stories of this, that if you give people an endless playground with endless storage and endless compute, if you don't manage it well, that it also can become a huge mess. And that cost can really get out of hand. I've seen and heard multiple examples of this. But and then sometimes the technology is blamed, but it's data management, right? You should set limits and caps and still think about. It's weird if we give every developer a 4XL Snowflake warehouse just because we can, because it will be really costly. This one I'll go over really, really quickly. It's one of the few benchmarks that I could find. So that's always a good thing, right? Go and how do I choose? I can do my own benchmark. You can find. Can I find a benchmark of these different systems on the internet? So this was one that I could find that was sort of honest, as in that the code of how they actually did the testing, it was open source. It was the code that they run to do the test was actually available on GitHub, so you could sort of cross-validate. And they explained how they did the testing, which is the TPCDS set of queries, but run in a way that actually in real life, if you run this in production, you would never run a query only once, and you would always use this kind of functionality, partitioning, clustering in real life. So here the question is what good is the fit in with the real life situation? The only thing that I can say, and that this test proves, is that what I said in the beginning, that costs and timings were sort of in the same range, right? So no orders of a magnitude difference. The others, there's only 3 systems that part of my comparison that on this test, the other ones were not. So summary of this. The problem with obviously these costs, and if you only look at the cost of compute, that is also not the total cost of ownership, right? One of the advantages I found with moving, for instance, one of my the customer I worked for, they went from on-premise Hadoop plus Vertica to Google BigQuery. Yeah, that saves a lot of time. There's basically one engineer from a small team that wasn't needed anymore, because somebody was fully dedicated on managing Hadoop and Vertica and all the things and new versions, disk space, whatever that comes with that. And a lot of these systems, one of the reasons to choose them is that kind of work, new versions. Where's my monitor? Oh, it's gone. It's gone. Doesn't matter. That it's that work disappears. So if you want to do that honest comparison, you shouldn't only look at the direct cost that you make for that. And if you indeed look at tests, and if you look up benchmarks, really look at how are these benchmarks actually done? Do they cover a real life scenario? one of the most important criteria that I personally think is, okay, if I'm choosing this system, what kind of functionality do I actually need? And here are some interesting things. For instance, imagine that you're building a data pipeline, and in the functionality that you use a lot of either regex expressions or geospatial functions. If that is, for instance, in your current code base, or it's important for your business, yeah, then this is basically out of the window, right? It's just not an option. Or, for instance, in my client, we said we know the structure of our data. We had a bit like what you had at your current client, a lot of different databases that were slightly different and multiple vendors. But what we actually did, that we connect them all to the same Snowflake instance. And because the schema and structure and content is slightly different, we first load it to a sort of JSON kind of, we almost use the first receiving layer as a sort of MongoDB. And for instance, Snowflake supports that really well. By the way, it stores JSON data and basically is the only one that does this from these systems. So, and then only that design pattern, the thing that you want to do, can become an important selection criteria. And so there are basically other things to choose from. Do you want to work with materialized views a lot or something like that? And these things and these features that you select, and here are even more of them, they can be different for you or your customer, right? You have to look at your company, what you do, your current code base, what is important for you, and maybe add a few. Another thing, I want to do something with machine learning, for instance. I want to keep it really simple. Redshift and BigQuery support in database machine learning training and prediction. If that is what you want, if that is very important for your use cases, then these two basically go out of the window. Okay, they can predict, but they cannot train. Depends on what you want, right? What is important about almost all these systems, things like replication, backups, new versions, configuration, maintenance work, are basically all, that's basically done. At the time, I had to be bothered with new SQL Server versions and service packs and space running out and tempDB and don't know what. That's just gone. I already said I like Snowflake for its simplicity that is not too simple, but just enough. BigQuery and Snowflake in functionality like things like supporting time travel. Anybody know what time travel is in databases? Yes? Yeah, it's basically sort of continuous backup. So basically any DML statement that you do of inserting, updating, whatever new data, you can basically do a select clause with a sort of at this moment in time and look at the state of the data as it was before that query or at that moment in time. So you have a form of continuous sort of backup, which can be really handy. And even some have functionality like undrop, right? If you drop a table schema or whatever, that you can undrop. And as such, for instance, at my current client, we don't back up the thing that we had before in the past, that you would back up your environment. We just don't do that with Snowflake because we have enough time travel set that that kind of risk is mitigated. Yeah, I already said especially if you're on the old Redshift still, then you should do something and start a project to migrate to a newer Redshift, but I'm not sure. One of the interesting things about all these systems is that they don't have enforced primary and foreign keys, which you always can find on OLTP systems, right? Operational databases enforced primary foreign keys. They're just, it's normal, right, that you have them there. And here they're not possible, and they're not possible because if these vendors would support that, that actually is a limiter for that scalability. Because if you think about it, making sure that if your data is spread over a large cluster with compute, that data from a table is actually unique, you basically need to, as soon as you add one new row, you need to go basically over all your data to make sure that it still is really true. And that's why they're never enforced there and probably never will be enforced. The fact that you choose with such a system comes with always with some sort of a cost. Which means, for instance, if you want to validate that something is unique or you have foreign keys, for instance, in my current client, if that's important and we use dbt to build our pipeline, we just add dbt tests that are basically just queries that validate at a certain point in time that you run the test where data is still unique or whether foreign keys exist. But it's more a form of lazy validation then, right? And one of the more negative things about Snowflake is because it's cloud independent and actually a competitor with Google's offering, with Amazon's offering, and with Microsoft's offering, that it just feels, and in real life is a little less integrated with the whole cloud ecosystem of those vendors. What's the consequence of this? And does this mean that all your work is gone? No. The competences that you need to build a good data warehouse, and that's a whole other story. What are those competencies? I won't go about that. They still exist, so you still need a good methodology to build a data warehouse. And stuff like partitioning and clustering, making sure that your data is physically laid out on that storage, you still have to think about that. That's one of the low-level work that still remains. But solution versions, maintenance, backup, that obviously goes away. And the last, privacy security. It's kind of simple. When I went about and started looking at all the pages and all the disclaimers and ISO certification, that in theory is not a problem. All can run in Europe. Most of them have data centers, even in the Netherlands. What is more interesting is, and this is my personal opinion, but this was, for instance, one of the reasons that my current client didn't want to go with that works with health data, that they didn't want to go with Google. I'm almost okay. That they didn't want to go with Google was basically this. So that has more to do with culture and how a company is perceived, right, than with tech. I mean, it's the same as your story, Sadie, that the reason to choose Java was, as I heard it, more related to politics and sort of making it easy to actually make that transition, right? So sometimes the reasons to choose something are not based on features and functionality, but on politics and feelings. That's just where we have to live with, right? But looking at private security, in theory, all is well. But a lot of companies still, well, compared to a few years ago, I do see more companies also with sensitive data. For instance, my customer going to the cloud, and so I think that fear is a little bit is way less than a few years back. That's at least my observation. So if you ask me, this would not surprising. I think these is my two top picks, but obviously that's only my opinion. I don't know enough about Databricks yet to, or haven't actually worked with it. Probably want to work with it first before I can be really opinionated about that. But that's my that's the two most flexible and versatile systems, I think. and then either one of these. And that's it. Questions? Speed.